All right, this is the first example for the graphical approach to describing a function. What we're going to do is a visual inspection of a graph and then describe it using the terms that were given in the previous video. You may need to do some approximations, so feel free to to the nearest, half a unit or possibly a quarter of a unit, but you don't have to be too precise, all right? So just going to estimate, for instance, this x-intercept, it does actually look like about 0.75 or 1.75 or so, but you just estimate to the best of your abilities is all I'm saying for this exercise. All right, I'm going to do this one example with you. And but if you wish to, you could pause the video right now and try and complete these different fields, and then turn the video back on to see the result. All right, so I'm going to begin with describing increasing and decreasing regions. All right, so increasing is our regions which are rising to the right. So I can see that the graph is rising to the right here. I'm going to color it in with some red just to kind of give it a little color coding. All right, so, and then at this point, it's no longer increasing. So if I was to describe that, the increasing region are the domain values of that region. So that starts at x equals -2, not including -2, of course, and it stops at x equals -1. So that's our first increasing region from -2 to -1. All right. And then I notice there's another portion of the graph that is increasing starting at x equals 1. And it increases up into this point, which is at x equals 2. So I have a second region, so I'll join those from 1 to 2. All right, so those are the increasing regions. All right, so now I'm going to do decreasing regions. I'll color those blue. All right, so I could see that there's just one in this section in the center is the decreasing region. It goes right through the origin and it connects the red regions. So the single decreasing region, the domain, starts at x equals -1 and it ends at x equals +1. So there is my decreasing region again. So remember that we answer these using domain intervals. All right, the next question asks for intercepts. So these are ordered pairs. These are locations. So the x-intercept could be stated as x equals, or it could be stated as an ordered pair. I'll be precise and state the ordered pair. So let me go ahead and color those x-intercepts black, just kind of highlight them. So here's an x-intercept, and y-intercept, and here's the x-intercept. All right, so let's state those. The first one is maybe that's about x equals -1.75, just estimating, comma 0. The second one is at the origin. So I just make a list. So isn't that different from stating a domain interval? We use this union symbol to concatenate these two regions. But here we're just making a list of locations, so I use a comma. And then the third point, third x-intercept is at about 1.75 maybe, comma 0. All right, only one y-intercept, otherwise it wouldn't be a function, right? So 0, comma 0. All right, so what's the domain? So that is asking for the x values for this entire region. And I can see that the furthest left we go is located at this point associated with -2, but this is not included in the domain. So I am starting at -2, but not including it. I use parentheses. And then the graph continues up until x equals 2. We see this endpoint, which is included in the domain. So I am going to enclose that in brackets. Of course, you can use inequalities. So we could use a compound inequality. Something like this is, of course, all right to do as well. Okay, so this is a choice. All right, range. All right, range is the set of y values included in this function. We do have endpoints, and on the right, we have the highest point. It seems to end at about the lattice up here at 3. I'm just going to estimate that to be about 3. And the lowest it goes is this point, but it's not included in the range. So that's at about y equals -3. So I would say the range is from -3, -3 up into +3. -3 is not included, but +3 is. If you wanted to use inequalities, you would write it something like this time using the letter y, right? Okay, so either way. All right, local extrema. Remember that those are locations of any peaks and valleys or endpoints within a region. So the local extrema here are, we do have an endpoint here, but it's not included in the domain, so it's not defined. We can't include that as a local extrema. However, we can include this endpoint, which is in the domain. So I will list that one. The location of that is at 2, 3. So that's one local extrema. The other one are at the peaks and valleys. So so this is a local max. This point right here is a local maximum for this domain. It's not the absolute maximum, but it is a local maximum. So I will list that point. And so that one is at -1, 2. All right, so the first 2 points that I've listed, these are called local maxima. Because they're high points or peaks in the graph. All right. If I wanted to say local, and by the way, what's another word for local? Do you remember from yesterday? We could also say relative. So relative maxima would be acceptable. So local, let me call it local minima or minimum. I think there's only one. So we have 2 points that seem to be low points, but again, remember the endpoint here is not in the domain. So I can't include that one, but I certainly could include this little valley area. So it's located at 1, -2. So local minimum at 1, -2. Okay, so I could have written sentences. There are local maxima of 3 and 2. And a local minimum of -2. I could have said something like that. There are different ways to state this. Let's look at global extrema, the highest and lowest points in the entire region. So we could use global as a word, or we could also say absolute. You'll see those used interchangeably. So absolute, and let me see, how about an absolute maximum? All right, there's 2 high points, but the one that's the highest is this endpoint, and that's located at 2, 3. So I could say there's an absolute max of 3 at x equals 2. That's a very common way to state it, or you could just state the ordered pair. Okay, and how about absolute minimum? The absolute lowest point of this graph. Oops, min. Absolute min. Well, I do have 2 low points, but however, this one certainly isn't the lowest. There is this section right here, which is lower. However, there's no absolute minimum because these points right here, as you take the limit as the y's are approaching this, they never seem to quite reach this point. They are actually always increasing to this point, but never quite get there. I can always give you, if you state a y value, say this y value here, which you think is the end, I can give you one a little bit closer to this open-ended. So there is no absolute minimum, none. So that's what happens when you have open-ended endpoints. Concavity. All right, so let's color code this one. Concavity. I'm going to do, let's see, what color should I do? I think I'll do green for concave up. So concave up, let's do up first. So I can see there's this bowl shape right here, all right? And literally I have to decide where the bowl begins and ends, right? So it looks like it's completely concave up on this region. So I think I'm going to include all of this to be bowl up. Okay, so and then it turns. I have to decide now where to end my bowl up. So do I end here at the origin or do I go a little bit further? So you have to make a decision here because we're estimating. We're not doing this analytically, we're just estimating. So I think I'm going to end right here at the origin, just making an estimate. So there's my bowl up region. So I list the domain values. So that is from x equals 0 to x equals 2. My concavity is up. Okay, so then I'm going to do concave down would be the next region. Let me change, let me highlight it in yellow. So concave down, so that's this region here. And so that's from x equals -2 to x equals 0, the origin. All right. Now, did I have a change in concavity? I certainly did, right? So that change occurred at the origin. That's where I decided to change. I'm not sure if that's where it changes. Could be up here a little bit, could be down here. I'm not sure, but it's somewhere in this region. I know concavity is changing from concave down to concave up. So I'm just going to call it at the origin. When we do this analytically, you're going to find a precise point. That's the cool thing about the analytical method is the precision. We're not estimating. All right. So that's example number 1. Now it's up to you to go try a couple more examples. So for instance, why don't you take a look at example 3, work these out yourself, again, doing some estimating. And then example number 3, so this is the third one. Try both of these in your notes and then come back to the next video and check out the answer.